Okay, so I'm going to quickly introduce you to some of the code that you find in Chapter 3. We have two different kinds of implementations for the unsorted type lists. One is an array-based implementation and one is a linked list-based implementation. So let me just quickly go through the files here to make sure that we're all on the same page in terms of how these implementations might work for one of the ADTs that you create or that you'll find in the textbook. So I'm going to jump back and forth a bit, but first of all I'm going to be looking at the file that actually runs the tests here. This is something that the book likes to do. It's what you might call a test harness. It basically is a file. It's a function. Here is in fact our main function on line 15 that runs this application. And basically what it does is it's going to open an input file that contains a list of commands that you want to test, and then it's going to open an output file to write the results out. So depending upon what you're testing, the input file is going to be different. In our case, it's going to be basically the names of the various methods and some arguments so that we can test to see if they are in fact running properly. This is kind of what you would call a basic bench testing of your code. So let me just quickly step through it. We pull in the standard includes. We're going to pull in the include for our array implementation, which is what we're examining first. And then I've also included the tools HPP that we standardly use. We're going to do a using namespace std so we don't have to preface a lot of the standard C++ with std::. Makes the syntax just a lot cleaner. Internally in here is a function called printlist, which is going to take the list and print it out to the output file. The actual this is the declaration. The definition is at the bottom of the file. So if we scroll up a bit here, and here is our main program. It's going to return a return code of an int. Here are the streams, input stream, output stream. We collect the file names for those. There's a label that we use to mark in the output file what it is, and then the command operation is what it's reading in from the file. Some other here is in fact the list, which is made up of a list of item types, and well, we'll see more of those as we go along. I added the banner from tools HPP so that we know who's running your output. It's going to ask for the input file command name, and in this case the input file is included for you. It's called driver data with a big D in the middle. I'll show you a run of this so you understand how this works. The name of the output file, this is whatever you want to call it. I'm calling it just out, and when I run it, it's going to keep appending to that file so you can keep using the same file name. Then you give it the name of a test run, which identifies what you're doing here. I'm going to say something about it being unsorted lists and an array implementation. And it's going to write that out. If it can't find the input file, it'll stop with a message. Otherwise, it's going to go into a loop that runs reading commands from the input file until it sees the command quit or it runs out of data. So you can see here, these, if you remember from our text, are the names of the methods of the unsorted list, particularly the array version. Though in fact at this level, and this shows you something about abstraction, the list driver is the same for both the array implementation and the linked list implementation. If the command in the file is put item, it's going to then initialize an item with a number so you can pass arguments. It's going to, for the list object, the main list object that you're doing things to. It's going to put an item with that item there, and if in fact if it succeeds properly, it's going to write this message that this thing is in the list now to the output file. And likewise, you'll see here, we don't need to go into the details of each of these. You can do the delete item method, you can do the get item method, and basically what it's doing here, I think you can see, is for get item, if it finds it, it's going to say it found it in the list, otherwise it's not found in the list. You can test the get length method, you can test the is full method, you can test the make empty method, print list, which will print it out, and in the case, this is the other case, the otherwise of the switch, that is, if it doesn't recognize the command from the input file as a valid one, it will print this is not a valid command. And then it will just keep a running total of the number of commands executed. If it's when you hit the bottom, it'll write out testing completed to the terminal, and it will close the input file, close the output file, and print our standard termination message. Print list down here, basically it's going to take a list that's been initialized and a data file to write it out to, and each component in the list will be written to the data file, and it will leave the data file open. So you can see these pre and post conditions are useful to understand what's going on. It does in fact another one of the methods on list, reset list, to set the pointer at the beginning, and then figures out how long the list is, and then uses a for loop to simply walk the list, getting in the next item until you hit the end of the list, which is based upon the length that got returned here. And then it closes the data file. So that's the basic mechanism for how this works. So let's look at the more interesting parts for how the ADT is actually implemented. The most important part is the unsorted type, which is actually the unsorted list. And let's take a quick look here. Line 12, whoops, let's go back up here. Let's see, where are we? Okay, so for the unsorted type, this is the constructor, creates a list with a length of 0. The method is full. It's going to say, ask the question, is the length the size of max items? Remember, this is the array implementation, so we set the max items at the very beginning. Get length, well, simply returns the property length from the object. Get item, these are the more interesting functions because they actually are doing something a little bit more interesting. Basically, you're going to try to get the item out of this list, and if it's found, it will also return in the variable, the reference variable found, either true or false. If it found it, this will say true, and it will also, as you can see, it returns an item of item type. So I won't go into the great details here because the book describes this and I described this some during the lectures, but basically you're going to keep track of, is there more to search, where are you in the list, and until you find the element that you're looking for, found is going to be considered false. So if you don't find it, found will return false, and you'll know that it wasn't there. So more to search is going to check whether you've hit the end of the list. Basically, get item does a while loop. It's going to check using the compared to function, which is an important part of searching for things. It's going to use these enumerated types, less, greater, or equal, and those are actually defined in let's see, they're defined in item type here. This is item type.h. There's where max items was specified. The relation type, this is an enum, so in other words these are integer values, but you refer to them as less, greater, and equal. And so here is when you're creating an item type, and remember the whole point behind item type is that it allows you to use different kinds of data in your list. So in other words, it makes your list more polymorphic, to use the fancy term. In other words, it can handle different kinds of data without having to be completely rewritten. Now, in fact, this is not something that you would normally see in C++, because as we'll see, C++ supports this concept of handling different kinds of data using the same functions, using something called templates. So C++ templates is something we're going to learn more about. So eventually you're not going to need to add this sort of thing. You can simply use the C++ templates that are baked in to the language itself. So if we go back to here, this is, as we said, this is where the less and greater than were defined. So this is where you're going to check whether it's less than, greater than, or equal. In this case, it's really more we're interested in equal, so that we can determine whether we found what we were looking for. And remember, this is get item, so get item is going to return the item, assuming that it's been found. Okay. Next one, make empty. That's pretty trivial. The idea is that it is going to create an empty list. It zeroes out the length. If you remember in the array implementation, that's how you can zero out the contents of a list. In other words, in the array, we're simply going to say it's has nothing in it, that is, its length is 0, and whatever is in the array currently, we're just going to ignore and overwrite at will. So put item, remember put item is going to put things, it doesn't have to worry about where to put them in the list because the list is not sorted. That's shown here. Delete item is going to search through the list and compare, and as soon as it's equal, basically what it's going to do is take that and remove it from the list. Unsorted type reset list is going to simply take the cursor that you're using to search or move through the list and set it to -1. That means in the context of this application, current pos -1 means you're in before the first element in the list. And then get next item is simply going to return the data at the next item that is pointed to by the current position. Okay, so that is I think pretty clear. Of course, is unsorted H and unsorted CPP go together. Unsorted H is the header file for this, and but the actual application code is living in unsorted CPP. So that's very common. Sometimes you actually do put small pieces of code, usually one-liners, inline code or something like that. Sometimes you'll see that in the H or HPP file, but generally speaking, the H file is for declarations and the CPP file that corresponds to it are for definitions. And those are two very specific terms. If you don't have a good handle on that, look them up. C++ declaration versus C++ definition, because they really do mean two different things. So I think that is most of the guts of how this works. Let me now do a run of it just to show you how this works. And in fact, the linked list implementation, which is coded differently, actually works, has essentially the same interface. In other words, that what we call the contract that the ADT provides to the client, to the user of the abstract data type, is essentially the same in both cases. And what's different, and this is one of the beauties of abstraction, is the underlying implementation is different, but the user of the data structure doesn't need to know anything about that. That's the implementer's job to take care of. So what we will do is, this is code blocks. There is a build and run command just to make sure that we're up to date here. Actually, it built, it went so fast that you didn't see it. It actually compiled and linked the code. So here is our list driver running, the main function in the list driver. Here is the name of the input command file. In both cases, it's called driver data, D-R-I-V-E-R data. That's true in both the linked list and the array version. I'll just call it the output file out. You can call it whatever you want, and it will write it out to the local directory. Enter the name of the test run. Here's where you can distinguish between the different kinds of tests. So I will say unsorted type, which is the name of the list. Now, one thing, because of the way that these are written, I didn't write these, so I want to use them as is. This is expecting a single string here for the name of the run that's going to be put into the output file. So if I want longer phrases, I need to make it into a single string. So unsorted type, I'll call it array use all uppercase, implementation, and this is what will get written to the top of the file with the results of the run. Now, this is going to happen very fast as soon as I hit the enter key, so you'll see a new window come up. And how this actually works for you depends upon the IDE you're using, or it may not actually even be a new window. But this is how it handles terminal windows or consoles in code blocks. So here you see the driver went through all of the commands. It was counting them, 1, 2, 3, 4, 5, 6, 7, etc. There happened to be 22 commands, one of which is the command is called, if you look at the contents of the driver data file, I'll open it for you just so you can see. The reason it says error is not a valid command is because there's actually a command in the file called error. And that's just simply to test the condition where it's can't find the command for the the data structure that you're using. So anyway, as soon as I hit, and I'm running on a Linux system, as soon as I hit enter, the console window will disappear, and that'll bring us back to where we were. I have, if you look here, I've added the file out to my code blocks so that I can open it, and here it is. So here is in fact the output from that run. As you see, there's the unsorted type array implementation, and here's the output that corresponds to what happened in the file. You can go back and look to see the stuff that's being written out by each of the commands, and you can use this. You can keep the way that this particular version works is you can keep running different versions of this. If you write it out to the same output file, it's in append mode, so it'll keep appending. You can keep everything in one file and simply have different runs with different headers. So that is the array-based version. If we change to the linked version, I'm not going to go through everything because much of it is the same. The big difference, of course, is the the implementation of the list as a linked list as opposed to an array. The previous one had the concept of max items and things like that, and it was actually statically declaring it, the array, at the beginning, and of course you could never have more than 5 items in the array because it's a static array. In this case, though, if you look at the version here of the unsorted, this is the guts, remember, the unsorted, this is the declaration, and unsorted CPP is the definition. So it uses the same item type concept. Again, that'll be replaced by templates in the future. Let's take a quick look here. So we have this concept, remember, from the lectures, we now have nodes, and we're going to link nodes together. The unsorted type has been modified to support the concept of nodes. Now you'll notice here, as we said in the lectures, that much of this is identical at this level. In other words, the interface hasn't really changed very much except in a couple of cases. So if you look at this and compare it to the array-based one, you'll notice that from the outside of the implementation, it looks virtually identical. That's not an accident. However, you've changed completely the underlying mechanism for storing things and manipulating things. So the real change here is in the unsorted CPP. So this is now we have no more arrays to be manipulated, but we have nodes and links and addresses. So here is the struct for the node type. These are our nodes. They have an info component, which is the actual data that you're storing of item type. So they could be ints or floats or whatever. Then we've got a pointer, that's the star there, to the next node or node type. So this is the guts of how we manipulate linked lists. There's a piece of data, and then there's at least one pointer. This would be a type of list, linked list, called a singly linked list, or SLL. There are, if you modify node type to include other information, which you easily could, you could have, let's say, a node type pointer to previous. And in that case, then of course you'd have to rewrite your code to maintain these links. However, you could then have a what is called a doubly linked list, or DLL. And in that case, when you move through the list, you could move in both directions. The examples we've seen so far in our singly linked list, which is what this is, you can only move from the head, the beginning, to the end, and you can't go backwards. However, as we'll see, there's actually a benefit to being able to go both directions. Anyway, so this is the simple case. So we have here's our class constructor for our linked list version of our list. Length 0, list data is null. Now that's again very different from the other one, because now what this is, list data in this code is what you call the head pointer, which is the address of the beginning of the list. So a list with no elements, you point at nothing. However, it does now exist as a list. It just happens to have no elements in it yet. So here are the other methods. Is full. Now this is different again in practice. Conceptually, you can ask the question, is full of the array. In that case, it's very easy to answer. If you're used up all the array slots and you're up to where your length is equal to your max items minus 1, then your array is your list is full. Here, this is a different underlying meaning of what is full means. Is full will only become true when you effectively run out of memory on your system or in the working memory space of your application. Because what happens here is the way that it determines is full is it attempts to create a new node, and if that fails, it will return false. Otherwise, it'll return true, because that the attempt to add a new type, which is what we're doing at line 23 here, new node type, if that fails, it throws a bad alloc exception. And that's the standard C++ exception when you run out of memory. So this is just a convenient way of testing whether you've run out of memory, which really shouldn't happen, and generally speaking, but it is conceivable. This is at least an elegant way of tracking whether that happened. Okay, so you see how it's actually doing it. It's not asking, is full, have we maxed out the total number of spaces in our array, since that concept doesn't exist, since we're dynamically allocating things. What's happening here is that you're trying to allocate a new node, and if you can't, it fails, throws an exception. However, if it does, you simply then delete it again. So it's kind of maybe a little funny way of thinking about it, but it's a kind of an elegant, easy way of testing whether you've run out of memory. Get length. This is a standard accessor, an observer in our book's terminology. It simply returns the value of length. Make empty. In this case, it's a little different. Make empty was very straightforward before with the array. In this case, what we do is we have to, and this is one of the places where the linked list implementation is actually, in terms of its complexity, this particular method is more complex, because with the make empty for the array, all you simply had to do was set the length to 0, and it's now, quote, empty, because you're ignoring everything after that. Here, however, you actually have to traverse the list. So in other words, you start with list data, the head pointer, and then basically what you're going to do is you're going to delete as you walk through the list. You're going to continually shorten it by looking at what you're pointing at, keeping track of what it's pointing at, then you delete the thing that you were just looking at, and you make the new head pointer the thing that what you just deleted was looking at. Okay, so if you follow that logic, basically you have to first capture what it is that you were, where the thing is that you're deleting was going next, hold on to that, then you can get rid of it. Okay, so but the issue with this from a theoretical standpoint or a complexity standpoint is you have to walk the entire list in order to do that. So this means it is order of n. Okay, so it's linear. Put item essentially is going, this is an unsorted list, so it doesn't make any difference where we put it. In this case, the cheapest thing to do, in other words, the least walking of the list, is to stick it in the front. Now this is not true, as you'll see later on in the case of the next chapter where you're doing sorted lists. There you cannot get away with simply tacking it onto the front. So in that case, the complexity of the sorted list, maintaining it is more complex. Here, get item. Okay, simply this is going to retrieve the item, and if it can find it, it will retrieve the item and give it to you. Otherwise, and this second reference variable found will be set to true. Otherwise, it will return false, and then you'll know that there's no item to look at. Okay. So basically, this works in the same principle as the the array-based one. In the array-based one, you simply walk through the subscripts. You incremented the index, and you looked at the next one. Then you looked at the next one, and you asked the question, is it equal, etc. Until you ran out. You hit the end of the list in terms of the length. Here, obviously, what you're doing is a little bit different. The more to search is not counting how many array locations there were, but it's looking for whether the pointer of the node that you're looking at is null. If that's true, we're at the end of the list, and so we know that we're done. Delete item. Delete item essentially it's the same thing, okay, except we're looking for is it equal, because that's really what we're interested in here. Is if we can find it being equal, it will delete the first one that it finds, and basically take whatever it was pointing at and making the previous thing. And this is where this gets a little tricky, because if you think about it, let's say you're in the middle of the list and you're walking along, you've got a pointer that points at a node, and then you say, that node is the one that has to be deleted. So what you want to do is remember the address of that guy, and then look where it was pointing, and then make the address of the thing that got you to that guy equal to the thing that the node that you're deleting was pointing at. Okay, this is not that difficult and a little hard to explain, but I think you get the idea. If you're going to remove an element, you have to be able to hang on to where the thing before it was, and you have to hang on to the address of the thing that it was pointing at, so that you can then fix the pointers and effectively update the list so that it is now minus the thing that you were attempting to delete, because you found it. And so and then of course, once you do that, once you've fixed up everything, you now have the node that you were attempting to delete, and of course you have to then physically delete it, because remember, this is C++. Nodes are being created using the new syntax, NEW syntax of C++, and that dynamic allocation. If you're doing it in your code, you have to then be responsible for removing it. Otherwise, you will wind up with memory leaks. Reset list, kind of like setting the current pos to -1 for the array. By default, if you set it to null, that means it's an empty list, so you're back at the beginning. Get next item. This is going to walk the list simply by walking along and looking for the next item. As soon as that's reached, the current pos is reset back to the beginning, and it returns the whatever the contents of the next thing was. Now here, this is something that I had mentioned. This is the if we saw the constructor at the top of this file for unsorted type, here in fact is the destructor, and this is the at line 142 here, the destructor for this, and the way that you can tell it's a destructor is by the tilde, okay, the little squiggle. It uses the same name as the class, but with the tilde in front, and that is going to get called when your variable goes out of scope, or when at any point in the program where it's going to be deleted, whether you delete it or whether it's deleted automatically by the compiler or the runtime system, that is. So here the trick is, again, you can't simply delete the list, in other words, delete the head pointer, because what that's going to do is, if you do that before you delete each member of the list one after the other, that is what this while loop is doing, you have to walk the list and delete them one by one. Here is your delete. This is actually deleting the dynamically allocated memory for that particular node. If you don't do this and you simply, delete or let the list pointer go out of scope, then all of the memory that you've allocated while you were creating the nodes is going to be left dangling out there, but the problem is there's nothing pointing at it anymore, so you have no way of getting at it. So this is one of the banes or chores that you have to deal with when you write code in C++, is you have to manage this yourself. As I said, other languages like Java don't force you to worry about this. They automatically do this, what you call garbage collection, because effectively this is your garbage from your application. So I think that is sufficient to show you the differences. There are more specifics again in the textbook if you didn't understand how these two things are different. Let me now run this version. From the outside, it's going to look virtually identical. Actually, it's going to be completely identical because the commands, remember the interface for this is the same to the outside world for the two versions, the array version and the linked list version. So in terms of doing this, both have the same commands and both should have the same output. And again, one of the beauties of abstraction is then the person who's using your code never has to know, in fact, that that's different. So here is the unsorted type linked list implementation. Okay, so there you would, if any of the commands didn't succeed, I'll show you what the commands actually are in a second, then you would see some output here. Okay, so in this case, this is our version of out. Here is the linked list implementation. Okay, here is the output from it. Okay, and just to clarify what is feeding this, this is the driver data input file that we've been using, and in fact it's identical for both versions, both the array version and the linked list version. And so it proves the point that the implementation is being encapsulated or hidden from the external view of the interface of your unsorted list. So we'll continue on with sorted lists. That will be more or less identical, except in a few cases, as you can imagine, where you have to maintain the sorting properly, and we will work on that at a different point. Hopefully you'll find this was useful, and I will be making the code here available to you as the basis for some of your assignments, which will be posted in the not too distant future. So anyway, hope that helps. If you have any questions, just contact me, email me, or call me, and good luck.